Hello, and welcome to the slightly late February webinar presentation by the Underground Construction Association's Younger Members Group. My name is Colin Sessions, and I am one of the members of the UCA Standing Committee for Younger Members. I am joined by Anthony Bauer, the Chair, Shannon Goff, the University Outreach Chair, Everett Litton, the Membership Chair, and Demetrio Kruscalo, the Media Chair. The UCA Younger Members is a standing committee of the UCA of SME. The Younger Members Group is a group of professionals of all ages who strive to attract and develop engineers and construction professionals under the age of 35. Each month we put on a free webinar on various tunneling topics. It's available for free to all interested parties. Before we begin this month's webinar, I have two quick announcements. Once again this year, the Youngest Members Group will be offering a scholarship for students to attend the RETC conference in June. There are a number of scholarships available, so I encourage anybody who's interested to check our website. In about the next 2 weeks, it should be posted. Or for those of you who aren't students, if you know anyone who might be interested, please let them know. Next month, if you logged in early, you'll see that John Hurt from Arup will be presenting on precast segmental tunnel lining design. So that should be a pretty interesting webinar, and I encourage everybody to register for that. Today, Mike Miller will be presenting on Indianapolis's DigIndy program. Mike has over 19 years of experience in the geotechnical engineering and construction industry. He holds both a bachelor's and a master's degree in civil engineering from Michigan State University and is a licensed professional engineer in Michigan and Indiana. Mike spent over 15 years with a Detroit-based geotechnical consulting firm prior to transitioning to his current role at Citizens Energy Group. In this role, Mike is the manager of construction in the Underground Engineering and Construction Group, where he oversees capital projects relating to water, wastewater, and Citizens DigIndy Deep Rock Tunnel program. Mike, thank you for presenting for us today, and when you're ready, please share your screen. It looks good, Mike.
Very well. Thank you, Colin, and thank you for that very kind introduction and this opportunity today. Excuse me. As mentioned, I'm Mike Miller with Citizens Energy Group in Indianapolis, Indiana, where I manage capital construction for our water distribution and wastewater collection systems, including our CSO abatement program, which we call DigIndy. Just a quick overview of today's presentation, which will primarily focus on why and what we're building and where we're at in our overall program. Consequently, this is a photo of our main beam tunnel boring machine being refurbished after mining the first 51,000 feet of our tunnel system, which I'll talk about in greater detail a little bit later on. Like over 800 cities in the U.S., Indianapolis is served by a combined sewer system, which I'll talk about in a moment. This photo is one of Indianapolis's CSO outfalls located along Fall Creek. The screens were added years ago in an attempt to keep debris from reaching the waterway during an overflow event. Obviously, this is not an ideal solution, not to mention it's a maintenance nightmare. But it is a glaring example of just how serious Indy CSO issues are. And just to set the tone for the rest of the presentation, I'm not a big fan of slides with lots of words, so I'm going to try to keep those to a minimum. But there will be a few, so please just bear with me for a few slides, and then we'll get into more of a show and tell mode a little bit later on. So quickly, for anyone that may not be familiar with a combined sewer system, I'll provide this brief explanation. Basically, during dry weather, a combined system collects and conveys sanitary flow from residents and businesses to a wastewater treatment plant, where the flow is treated and released into a water body. However, during wet weather, the combined system also collects storm flow, and in many cases in our northern cities, snowmelt, which combines with the sanitary flow. During certain size weather events, system becomes overwhelmed, and rather than backing up through storm grates and into basements, combined flow is released to a water body. So here's a brief snapshot of Indy's combined system. It consists of about a 55-mile square mile area, and directly affects 8 area waterways. Each of the black dots represents a CSO outfall structure, and there are 134 of them in our system. Each year, there's an average of approximately 60 overflow events, spilling about 6 billion gallons of combined sewage into our waterways. Just to provide a little perspective, if we considered Indy's professional football stadium to be a vessel, we would have to fill it up 16 times to equal approximately 6 billion gallons. And not to mention, portions of our system are so overwhelmed that as little as a quarter inch of rain in certain parts of town can trigger an overflow event. And I just want to add, Indianapolis is not alone here. There are over 100 CSO communities in Indiana and over 800 in the U.S. The graphic to the right is interesting, as we can see CSO systems were much more popular in early development of the eastern half of the United States. So I've defined the problem. Now, what are we going to do about it? Just a little bit of background here. CSO abatement actually stemmed from the Clean Water Act. Ultimately, CSO communities must enter into some form of settlement with the Department of Justice and the EPA. Usually those agreements come in the form of a consent decree. A consent decree is a settlement binding a CSO community to comply with the EPA's CSO control policy. And what I'll be concentrating on for the rest of this presentation is our long-term control plan, which lays out our DigIndy system, as well as the time frame for which we have to complete it. And finally, one other quick point before we get into the fun stuff. The City of Indianapolis entered into their consent decree in 2006. But what is unique to Indianapolis' situation is that in 2011, Citizens Energy Group purchased the water and wastewater assets from the city. Per the terms of that purchase, Citizens became liable to comply with the terms of the consent decree, but the city actually remained party to the agreement as well. So it's actually in their best interest for Citizens to successfully comply with the consent decree. And Citizens is somewhat of a unique entity in that we are a public charitable trust. In fact, we are the only public charitable trust that provides utility service in the United States. And the important takeaway here is that we exist solely to provide utility service to the residents of Central Indiana. And we're basically a private company that operates on a zero profit basis, so we don't have shareholders to answer to. And this is especially important when considering that we can procure projects outside of traditional municipal bidding laws, and I'll provide some examples of that in a few minutes. As I previously mentioned, our long-term control plan was actually developed under the City of Indianapolis and their team of consultants, and Citizens inherited it in 2011. However, it does continue to evolve. Basically, there were a number of early action projects which utilized modified flow control or inline storage to take advantage of areas in the system that had excess capacity. And those projects actually eliminated a significant amount of CSO volume from entering our waterways. However, as mentioned, we still have about 6 billion gallons of overflow volume per year. So the remainder of our long-term control plan consists of upgrading our 2 advanced wastewater treatment plants, which has been completed to date. And those plants need upgrading in anticipation of the modification to our system and the additional flow that will result from construction of our storage and conveyance system. And as an aside, the picture on the left was taken while I was walking along the White River the morning after a CSO event. You can see the lingering debris and sheen produced by that event. So hopefully I can take that same picture in a few years from now with a little bit different outcome. So here we go with, as a construction guy, is the fun stuff, in my opinion. So what we're looking at here is the backbone of our DigIndy program. In order to prevent CSOs from entering our waterways during an event, flow will be diverted into our deep tunnel system, where it will ultimately be stored during the event and pumped out and treated. The system consists of 6 interconnected deep rock tunnels, which will be 18 feet in finished diameter when complete. The entire system will convey flow from north to south via gravity, where it will end up at our Southport Advanced Wastewater Treatment Plant. So while we do have 2 treatment plants serving Indianapolis, all of the tunnel flow and all of the CSO flow connected to the tunnel system will be conveyed strictly to our Southport plant. But after a CSO event, the flow will be stored in the tunnel, and then it will be lifted by a 90 million per gallon day pump station almost 300 feet vertically up into the plant. The entire system has a storage capacity of well over 250 million gallons per event, and that will allow us to comply with our consent decree terms, which requires 95% capture by volume. everywhere in the system except Fall Creek, which is the green line, represented by the green line at the top of the graphic. In our Fall Creek area, we are required to capture 97% of CSO volume CSO by volume. So flow will be diverted from CSO outfall structures and consolidated through soft ground surface sewers, where we'll enter one of 33 planned drop shafts. The drop shafts extend down into deaeration chambers, which are connected to the main tunnel through smaller tunnels referred to as adits. And depending on where the drop shafts are located with respect to the main tunnel, the adit lengths in our system can vary from a few feet to hundreds of feet. At each drop shaft location, we also have a vent shaft that extends down into the deaeration chamber. And the vent shafts are necessary because we utilize tangential vortex drop shafts, which entrain a great deal of air as flow falls down the drop shaft. The deaeration chambers allow for the air to escape rather than inhibit filling of the deaeration chamber and tunnel. Our design team spent a great deal of time studying different drop shaft scenarios, including extensive physical modeling at the Iowa Institute of Hydraulic Research as well as Auburn University. The photo on the right was taken during a visit to Iowa to view some of the physical modeling that they were performing for us. And I mentioned earlier that we have 134 CSO outfalls in the system. The tunnel won't capture all of them, but we will be consolidating approximately 100 of them into 33 drop shafts. We want to keep the number of drop shafts down to a minimum due to the cost to construct and the surface disruption, and we're actually studying eliminating 2 of them along our Pleasant Run alignment as we speak. So I mentioned the program is constantly evolving. And because I mentioned the deaeration chambers and vent shafts, I want to take a quick second to discuss tunnel ventilation with respect to air exiting the main tunnel during filling. I mentioned we have about 250 million gallons of storage capacity, and when it's empty, it's full of 250 million gallons of air. So on the right is a screenshot of our transient flow model, and you'll notice that during our design storm, the tunnel system fills from the middle. This actually traps a massive amount of bubble, which I lovingly refer to as the tunnel burp, at the downstream end of our tunnel. And as filling continues, this bubble will be forced upstream along the crown of the tunnel, where it will eventually exit at the first few shafts it encounters. Our issue is that the first couple of shafts are small diameter utility access shafts, and the velocity and violence that the air exits will cause geysering. We know that other systems, including Chicago's TARP system, has had real issues with geysering, and they've actually experienced geysering events so violent that manhole structures have been blown out of the ground. So we've done extensive research and physical modeling to understand this phenomenon, and to prevent geysering in our system, we're actually going to seal off our utility shafts where they intersect the tunnel, forcing the tunnel burp up to one of our larger diameter tunnel working shafts. And we're also building bulkheads along the crown of the tunnel at a few of our branches to keep air from heading towards dead ends and directing it to larger diameter shafts. So this is an ongoing study, and as we speak, our design team is actually receiving a big update from our modeling consultant on this very issue. Pretty interesting stuff, and as you can see from the photos on the slide, this is serious. This is one of the more famous tunnel geysering issues, and you can see this video on YouTube. So I talked a lot about the number of shaft locations that we have to build, and that really is where the surface disruption and the visibility of our program is going to come into play. The map here represents each of our drop shaft locations as well as our deep tunnel working shafts. And just to provide a little perspective and space, the yellow line, our Lower Pogues Run Tunnel, runs right through downtown Indianapolis. And interestingly enough, the 28 miles of deep tunnel that we're constructing is minimally impactful to the community. They don't see it, but it's the miles and miles of shallow consolidation sewers and the drop shaft sites which are extremely disruptive to residents, schools, business, and traffic. The photo on the right shows a 110-foot tall steel can being placed through a slurry-supported drilled shaft through the overburdened soils down to the top of rock at one of our White River Tunnel drop shaft sites. This particular site is located in the city park, but this type of construction is also occurring in residential neighborhoods and highly urbanized areas. Therefore, community partnerships and outreach is imperative to a project like this. We have a whole team of folks that work to form relationships and educate literally thousands of stakeholders impacted by the tunnel construction. We also have a team of real estate professionals dedicated to the land acquisition necessary to construct a program of this magnitude. And obviously, designing and constructing a project like this isn't possible without poking a few holes in the ground, especially since it spreads out over 28 miles. So I won't spend a lot of time talking about the geotech, but it is important to note just how extensive a quality geotechnical program is for this size of a project. And I'll add that this geotech program is still evolving. We're actually getting ready to mobilize to perform a number of deep confirmatory borings for a couple of our future tunnel sites in the next month or so. So the actual drilling program started back in 2005, which means we've had active investigations ongoing for over 12 years now, which is pretty amazing. And you can imagine we collect a lot of samples with that many borings and the extent of the investigation. So here's just a shot of a part of our rock core storage warehouse. And another view of the other half of the warehouse with cores laid out. This was actually during a procurement event for our first tunnel project where contractors and their engineers were welcome to view the cores. So what did we find? Basically, on average, we have about 100 feet of glacial outwash over the top of our bedrock in the Indianapolis area. And we have a high groundwater table, which makes construction through pervious overburden very challenging. And with respect to our rock, well, as the last bullet point points out, we have really favorable rock for tunneling. It's strong, but it's not overly hard or abrasive. And then here's just a representative illustration of our geology. We have Devonian and Silurian carbonate rock underlying most of Indianapolis. The shallowest bedrock formation along much of the alignment is the New Albany Shale, which is of the Devonian and Mississippian geologic age. And then underlying that shale, our carbonate formations consist of North Vernon limestone, Vernon Fork limestone, and Genevan dolomite, and the Wabash dolomite. And I realize this is probably a little difficult to read, but we do have an aggregate mine within close proximity to the tunnel project. So just another representation of the area geology. And we also do have the potential for some karstic features, which can and do make water. We've never encountered one this large in the tunnel bore, but I've seen a few in the sidewalls of the tunnel that are actually on the order of a few feet in diameter. So now I will transition over and spend some time discussing where we're actually at with the construction side of our program. Based on the terms of the consent decree, we have a staged construction schedule. This allows us to spread out the construction effort and spend over time while still bringing parts of the tunnel system online early in order to gain beneficial use and start getting CSO flows out of the waterways as soon as possible. For example, when we bring the Deep Rock Tunnel Connector and Eagle Creek Deep Tunnel online later this year, we'll begin capturing about 1.3 billion gallons of CSO annually. And then when White River Tunnel and Lower Pogues Run tunnels come online at the end of 2021, we'll experience a huge increase in that annual capture. So beneficial use before the end of the program is a big deal to us, and it also demonstrates to our ratepayers who ultimately fund this project that we are making steady progress and we are recognizing environmental benefits along the way. And I want to quickly point out that since construction commenced in January of 2012, we've received a lot of favorable press, both nationally and internationally. And in fact, our project was recognized by ITA in 2015, which was a big honor. Of course, this is a testament to our engineering team and contractor. As an owner, we remain very humble and understand that without a huge team of talented people, success of this program wouldn't be possible. So now I'm going to take us on a little trip along the alignment. For perspective, the red arrow shows the location of our Southport treatment plant, which is the southern terminus and extreme downstream end of the entire system. It is the location of our deep tunnel pump station, as well as the launch shaft site for the first two legs of our tunnel system, the Deep Rock Tunnel Connector and the Eagle Creek Deep Tunnel. So those will be the two tunnels that we'll concentrate on for much of the remainder of this presentation. And I just want to take a second. I keep saying deep, so I want to provide some perspective to what our definition of deep is relative to our system. On the right is a schematic showing the end of the line of our tunnel system and its connection to our deep pump station. So if we were to place the Statue of Liberty in the bottom of our pump station, only her torch would stick out of the top of the shaft. So that's just a little reference for what deep means with respect to our tunnel. And I'll also point out that the schematic on the right shows 2 shafts down to the tunnel prior to the connector tunnel to the pump station, and that will be important in the next slide. So here's a closer look at our pump station. And again, to reiterate, following a wet weather event, when the pump station is activated, CSO will enter the screen and grit shaft through the 18-foot diameter tunnel, or it will flow through a bar screen on its way through a 6-foot diameter connector tunnel. The connector tunnel feeds a 6-foot diameter suction header, which is connected to 4 30 MGD pumps. The station is rated at 90 million gallons per day, so 3 pumps with 1 in reserve. Flow is lifted by the pumps up twin 42-inch discharge lines, where it is then conveyed to the treatment plant via gravity. One thing I'd like to point out, that the original tunnel launch shaft on the screen and the screen and grit shaft were 2 different structures as shown on the previous slide. However, through a value engineering exercise, the dedicated screen and grit structure was eliminated, and the tunnel launch shaft was converted into the screen and grit shaft after completion of the tunnel. This saved an estimated $8 to $10 million, and anywhere along our system that we can eliminate tunnel working shafts or drop shafts, we have done so, which adds up to huge savings over the course of the program. And for you mechanically inclined folks listening today, here are some of the stats on our pumps. I'll also mention that our pump station contractor is a joint venture between Oscar Renda and Southland, both out of Texas. The pump station project commenced in mid-2014 and is expected to come online by the end of this year. So now just some show and tell. This is a shot of the cavern during excavation. The cavern itself is a horseshoe configuration. It's about 60 feet wide and about 75 feet high to the crown. And front to back, it's about 100 feet or so. And you can get some perspective of scale with the workers in the background. You can also see the main access shaft into the cavern, which is 35 feet in finished diameter. Just another couple of shots during construction. On the photo on the right, you can actually see the equipment shaft near the crown in the upper left-hand corner of the photo. And a little bit further along in construction, I should mention this shaft was excavated using drill and shoot methods. It took about 90 individual shots to excavate the approximately 16,000 cubic yard area. Also, the shaft walls and crown are supported by over 700 rock bolts, and the exposed rock face is covered in shotcrete. And here's a shot from about 8 weeks ago with the pump set and the bridge crane installed, and you can see the HVAC equipment going in, but lots to still do. And here's a shot from last week with the upper slab constructed and the pump motor set. So good progress as we continue to plug away on that project. On the left, you can see the header system where it ties into the connector tunnel. And on the right, you can see the connector tunnel, which leads to the screen and grit shaft. The finished 6-foot diameter connector tunnel will be cast in place reinforced concrete once complete, and it was constructed using drill and shoot methods as well. And then on the left-hand side is our tunnel launch shaft prior to the screen and grit build-out. This was after mining was complete and the tunneling contractor demobilized from this shaft. And on the right, you can see the guide walls that have been cast, which house 2 sets of guides for the rake mechanism that cleans the screens and the grit clam bucket to travel up and down. And finally, on the pump station, the photo on the right is taken in the bottom of the screen and grit shaft looking up to where the 18-foot diameter deep rock tunnel terminates into the shaft. This is the proverbial end of the line for the entire tunnel system. And as mentioned, we anticipate bringing the pump station online later this fall. So now we'll travel over to our deep rock tunnel connector project, which again is shown by the tan line, and the Eagle Creek Deep Tunnel, which is shown by the red line. And these are the first 2 legs of our DigIndy Tunnel System. The project was originally awarded just as the Deep Rock Tunnel Connector, as the Eagle Creek concept was for a shallow interceptor that was to be solicited at a later time. However, that shallow interceptor was a very high-risk project that extended open-cut construction through a business corridor, a residential neighborhood, and the city's levee and flood control system. Our contractor was actually aware of that future soft ground project, but they proposed the idea of making it a deep rock tunnel to mitigate the risk from the soft ground option. So their proposal included backing the tunnel boring machine up after finishing the deep rock tunnel connector drive and then relaunching it up the Eagle Creek alignment underground without the need for an additional shaft. This concept was very innovative, and we worked with our engineers to fast track a design. We had to go out and get additional geotech, obviously work with our permitting agencies. In about 5 months or so, we went from inception of the idea or conception of the idea to actually mining. So it was a really quick turnaround in a big effort. But we were able to actually construct that Eagle Creek deep tunnel for less than the soft ground concept in the end. And due to the additional storage volume of 17 million gallons that the Eagle Creek leg provided us, we were able to eliminate about another $15 million in planned infrastructure that was downstream from this area. So just a few of the vital project stats. I'll point out that the original contract award was for $182 million, but the Eagle Creek Deep Tunnel resulted in a $38 million change order to arrive at the $220 million shown here. I mentioned earlier that we are somewhat of a unique entity in that we are private, and so sometimes you have the advantage of being able to do things like a fast-track $38 million change order. So for us and our ratepayers, and as well as the environmental impacts that change had, it's a huge benefit at times. And of course, it would not be an official tunnel project without the obligatory cutterhead photo with the mayor and other project dignitaries prior to lowering the cutterhead down into the launch shaft. And speaking of the cutterhead, our contractor is using a Robbins main beam tunnel boring machine. In an effort to save a little time, I won't show the animation, but I will encourage everyone to check it out on YouTube later. And just a couple of interesting facts about our TBM, which is actually 40 years old and has been refurbished multiple times. It spent most of its life in New York and was most recently part of the Second Avenue subway project. And one thing I'll call attention to is that our TBM produces approximately 20 cubic yards of loose rock spoils per foot of advancement. So basically, one triaxial dump truck leaves the site full per foot of tunnel mined. Pretty amazing considering that the first 2 tunnel legs were about 51,000 feet. So that is a lot of truck trips and a lot of diesel fuel. And I'll also point out that our contractor and this TBM achieved 3 mining world records for hard rock TBMs between 20 and 23 feet in diameter. This is a testament to the design of the cutter head, which Robbins made specifically for this project. The refurbishment of the machine itself, obviously the contractor's forces, and the quality of our rock that I mentioned earlier. The contractor claims on future projects in Indianapolis they will break these, so we will stay tuned. So here's a nice photo taken by one of the folks from the Robbins company on one of their many visits to the site. This is our launch shaft, which consists of a slurry wall shaft through the overburden, about 100 feet deep, and then a cast-in-place concrete liner through the rock, which was excavated using drill and shoot methods. You can see our conveyor system, which Robbins claims is the longest one they've ever designed based on the number and degree of curves along the DRTC alignment. Obviously, there's probably hundreds of continuous conveyors longer, but adding multiple 90-degree curves and reverse radius S curves adds lots of challenges. It was really an engineering masterpiece, but it did take a lot of TLC as the tunnel boring machine got out 5, 6, and 7 miles from the shaft. In fact, the further out we got, I would venture a guess that the conveyor system was probably the limiting factor to the TBM production rate, but it did operate very well over the 7.8 miles of that first alignment. And we saw the photo on the left earlier, but to add some perspective, the upper shaft is 40 feet in diameter, and that lower shaft is 35 feet in diameter. And you can notice the exposed slurry walls, which form the upper shaft. And that is the permanent structure. Those will not be shotcrete or concreted. And we don't have an elevator or a stairwell, so the crane and cage is our only means of access down into our tunnel system. Just a couple of nice shots of the bottom of the shafts with the tail tunnel visible in the photo on the right. And so after the main shaft was constructed, the contractor then constructed a 500-foot long starter tunnel in order to assemble the TBM underground. It was about 24 feet high and was excavated in a horseshoe configuration using drill and shoot techniques. In the foreground, you can see the false walls that were necessary to allow the TBM's gripper pads to react against during the initial mining launch. And this is what our mine tunnel looks like. The photo is taken right at the transition from the starter tunnel to the mines tunnel. And you'll notice that primary support is by really a modest rock bolting pattern along the crown. And of course, you have all of the various utilities required to support the tunnel boring machine. And here's one of our many curves that I referenced earlier, which does challenge the conveyor system, as it is a very, very long rubber band that wants to be in a straight line, not go around curves. So we'll take a quick trip up to our Eagle Creek Deep Tunnel alignment. We have the DRTC alignment to the right and the Eagle Creek Deep Tunnel to the left. So as the TBM reached the upstream terminus of Eagle Creek, which was about 9,200 feet from where this photo was taken, it was actually backed down to this bifurcation and then walked about 11,000 feet back up to the Deep Rock Tunnel connector alignment, which was previously mined, and it was parked underground about 500 feet past the retrieval shaft. And I do want to point out that this is exposed rock, pre-concrete liner, and this just is another reminder of how lucky we are from a geological standpoint. And I mentioned earlier that once mining is complete, all of the tunnels will be lined with concrete. So here's a shot of the concrete lining formwork, and perhaps it's the nerd in me, but for some reason, whenever I see this, it reminds me of the Millennial Falcon. But I digress. So the lining operation was absolutely amazing. Once the contractor got in a groove, they could form, pour, clean up, strip forms, and relocate forms in a 24-hour period. So they formed and poured 240 feet of liner per day, which required up to about 600 cubic yards of concrete per pour. Concrete was pumped from the ground surface through various shafts and drop holes and could be pumped up to 3,500 feet horizontally in either direction from a single drop hole. And here's the finished product. Over the course of the first two tunnels, the contractor placed about 130,000 cubic yards of concrete. And following the concreting operations ongoing right now, the contractor is performing post-lining grouting through the areas where inflow is beyond specified limits. Earlier I described the vortex drops in the deaeration chambers, so here's a shot of the concrete formwork in one of the deaeration chambers. And this is very difficult handwork, 250 feet underground in very tight space. This is some of the slower work and some of the more expensive work. So again, where we can eliminate drop shafts and deaeration chambers, it saves time and money, but these guys do a really good job in very tight quarters. And here's a shot of one of the adit tunnels prior to lining. The adits, again, connect the deaeration chambers to the main tunnel. In fact, you can see the main tunnel lit up at the end of this adit. And once the deaeration chambers are complete, they are connected to the main tunnel through the adits with Hobos pipe. And a quick couple of slides describing how our drop and vent shafts are constructed using raise bore methods through rock. Through the soil overburden, we obviously have to use top-down methods like the slurry drilling and steel can support I showed earlier in the presentation. But we actually did build a few shafts early on through the rock using top-down methods, but they were very expensive and cumbersome and also time-consuming. One of the other issues is top-down rock drilling of this magnitude takes up a lot of real estate on the ground surface. But if you're not familiar with the raise bore method, it's a bottom-up excavation method, which is extremely efficient. The graphic illustrates the method in its simplest form, but a pilot hole is drilled, the pilot bit is taken off, a reaming bit is attached, and then the reamer is turned as it advances back up and rock falls into the tunnel where it's collected and disposed of. The raise bore method as I mentioned, requires a much smaller footprint on the surface than top-down methods. And on the left, you can see the raised bore rig, and on the right, you can see the reamer getting ready to make its journey to the surface. This method worked so well on our first 2 tunnels, we actually specified it as the only acceptable method on our 4 future tunnels. The only caveat is that the tunnel and deaeration shapers have to be mined and excavated first, which can affect construction sequencing if you don't have an adequate amount of schedule. For the future work, the tunnel contractor will be responsible for constructing the shafts to the surface, but we will solicit separate packages for the consolidation sewer work and surface connections to those shafts. This actually allows local contractors a chance to get at some of our work on our program, beyond the highly specialized tunneling packages that typically go to the big national guys from out of town. Now I want to head up the Deep Rock Tunnel Connector Retrieval Shaft, which is also our White River Tunnel Launch Shaft. As I mentioned earlier, the TBM was parked about 500 feet past the retrieval shaft. This was done to get a head start on the starter tunnel for the White River Tunnel alignment. The contractor elected not to excavate the shaft down to the design invert in order to allow the gripper pad something to react against as the machine mined through the shaft and out the other side. Upon initial breakthrough, the contractor actually mined about halfway into the shaft and then back to the TBM up to the face, strictly for this photo opportunity, actually. But that made the owner really happy, as well as the media, and I think the tunnelers' forces got a kick out of having a nice hole-through party. And mining into the shaft and backing up provided a very interesting view of the rock face, which you don't normally get. And it shows just how the disc cutters score the rock in a radial pattern as our tunnel boring machine cutter head advances. And here's a cool shot you do not get to see very often. This is our tunnel boring machine actively mining through the shaft while partially exposed. Again, it drove about another 500 feet past that shaft where it was parked underground. And just to put closure to the Deep Rock Tunnel Connector and Eagle Creek Deep Tunnel projects, we anticipate substantial completion will be achieved by May of this year. So a couple months, we're really rounding third on those projects. And one of the last tasks we have to complete is installation of fiber optic cable through the tunnel system, which will connect all of the tunnel instrumentation, the remote screen and gate structures, and both of our treatment plants. So as we have been busy constructing the first 2 legs of the tunnel and the pump station, in 2015 we held a solicitation event for the construction of our next 2 legs of the tunnel system, the White River and Lower Pogues Run tunnels. The tunnels had to be packaged together because mining is going to progress up the White River alignment, which is shown in light blue. But then the TBM will veer off and mine the Lower Pogues Run tunnel alignment, which is shown in yellow. Similar to the Eagle Creek tunnel, once the terminus of the Lower Pogues Run tunnel is reached, the tunnel boring machine will be back down the mined tunnel and relaunched underground back up the White River alignment. This same scenario will be executed again when the contractor mines the dead end hook portion of the White River alignment visible to the northwest. We learned a lot of lessons about backing up the TBM on the Eagle Creek Deep Tunnel, which actually allowed us to eliminate a retrieval shaft at the end of Lower Pogues Run. Being able to back up is really a strong tool in our toolbox, and it has allowed us to do some great things, especially from a scheduling standpoint. So I might even venture a guess that when our program is over, this TBM will perhaps hold a world record for total feet backed up by a TBM as well. So based on the proposals during that 2015 solicitation that I mentioned, we awarded the project to our incumbent contractor, the Shea Kiewit Joint Venture. We also did something pretty unique in that solicitation. We included non-mandatory alternates for guaranteed maximum pricing strategies for our future Fall Creek and Pleasant Run tunnels, which were still actually under design at the time. Based on the contractor's proposal, we did actually award the additional tunnels, even though they were not completely designed yet. So while I'm showing $200 million on the slide, the actual contract value for all 4 tunnels is closer to $500 million, with an approximately, I'm guessing, $300 million left in surface work that we will solicit to others. So we have our tunneling contractor on the hook for the remainder of our entire system, which includes over 18 miles of tunnels to go, and that is a huge relief from an owner standpoint. So after about 6 months of post-award negotiation, we executed the contract, and this project actually kicked off in mid-2016. And the yellow arrow indicates approximately where the tunnel boring is currently located as of today, which consequently is just outside the front door of our football stadium, Lucas Oil Stadium. And I'm going back to this slide to demonstrate the number of surface sites that we're going to impact over the course of our program. I want to draw your attention to one of those sites in particular located on our White River tunnel alignment. In fact, it's the end of the line of the hook I referred to earlier. But this is an example of collaboration with third-party stakeholders. Because our program is so long, and in some cases locations identified during design are very different than when you actually arrive to build something, it's imperative to be flexible and keep in close communication with all parties involved. In this case, the city of Indianapolis and a large real estate developer were going to transform Indy's old minor league baseball park into luxury condominiums. However, we had identified a portion of that property as the location for a drop shaft, as it was located near 2 large CSOs on our system. So we actually fast-tracked the design and construction of that particular infrastructure and constructed it almost 7 years ahead of when the tunnel will actually connect to it. This is one of those cases where we had to use top-down shaft construction methods through the rock down to the tunnel elevation, and part of the reason we don't want to do it anymore is the experience we had on these a couple of these early projects. But we were able to get in and out without delaying the development, and future tunnel connections will be made underground once the tunnel alignment extends to that point, so we don't have any future surface disruption in this area. And here's a shot of the completed development in the background and our infrastructure in the foreground. And while construction disruption is very large, the infrastructure we leave behind is very discrete. This is one example of a couple of projects we've actually had to go out and build ahead of our original schedule in order to accommodate external stakeholders, but from a community standpoint, it is the right thing to do. And to wrap up here, just a quick peek at what's next. I already mentioned the White River and Lower Pogues Run tunnel status, but here you can see all 4 of our remaining tunnels that will be constructed by the Shea-Kiewit joint venture with respect to one another. Once the tunnel boring machine reaches the end of the light blue line, the White River tunnel, it will then continue on mining the Fall Creek tunnel, where we will have a retrieval shaft at the end of Fall Creek, and that tunnel boring machine will be disassembled, brought to the ground surface, and it will undergo another full refurbishment prior to remobilizing it and mining our Pleasant Run tunnel, because that Pleasant Run tunnel is another 7.3 miles, 7.4 miles of tunnel. So just to make sure that machine will get us to the end, we do have another refurbishment planned. So to date, anything with a red circle around it is either complete or in progress, with over 30 surface sites remaining. Again, we've been lucky in the fact that our sites thus far have generally been in larger areas or industrial areas, but we are really getting to highly urbanized areas, and we're going to be impacting a lot of those previously mentioned stakeholders. But and on the right, you can see the approximate status of all of the major elements of our program. So overall, including early action projects and the treatment plant upgrades, our program is estimated at about $2.1 billion. However, with continual value engineering strategies, a number of which I mentioned today, we feel we'll be closer to about $1.8 billion, and hopefully over the next 8 or 9 years we can drive that number even lower. With that, I will slide into home here with the obligatory Cutterhead Mayor dignitary photo, which was recently taken when we relaunched the White River Lower Pogues Run Tunnel project. Consequently, the mayor, who is the gentleman in the middle on the upper right photo, next to yours truly, is not the same mayor as was in the previous project photo, but that is what happens when you have a construction project that spans over 13 years. You do have a lot of change of personnel, and that can actually impact your project. So again, as I mentioned earlier, community and stakeholder outreach and continuous communication is imperative to the success of a project like this. And finally, props to Citizens DigIndy Design and Construction team shown here, as well as all of our valued partners. And with that, I will take a breath and say thank you very much for your attention and patience.
Mike, thanks so much for that wonderful presentation. We'd like to invite all of our attendees to use the chat panel to submit any questions you may have, and we'll go ahead and read them off and capture those in today's recording. Since we're recording today's session, I want to remind everybody that this video will actually be available on the UCA Young Members website within about 48 hours. So go ahead and use that chat panel to submit questions. And Mike, I just had to say, I was so glad to hear that the TBM was going to be refurbished and continued for use in this project, considering it's broken all those records. It's famous.
It is, and what's amazing about it was close to 40 years old by the time we even got it. So our contractor actually performed the majority of the refurbishment themselves with assistance from Robbins, and the cutter head, as I mentioned, was specifically designed for this project.
That's great. I'll be sure to share that video from the Robbins TBM on the UCA Facebook page. I love those animation videos of the TBMs. They're really awesome.
Yeah, and that one is spot on for the type of TBM we use with that main beam system.
Great. It doesn't look like we have any questions coming in right now. Mike, would you like to make a closing statement?
I just really appreciate all of the time that everyone sat and listened to me ramble for the last couple of minutes today, as well as the support and recognition for our project. It is one of the larger tunneling projects in the U.S. right now, so we are happy to show it off. And if I can get a plug in, I will be at No Dig in a couple of weeks, actually giving a dedicated presentation regarding strictly the solicitation of the 4 projects that I talked about that we bundled together, just because that was unique to be able to take the approach that we took. So that'll be in Washington, D.C. in a couple of weeks.
That's great. We've had a question come in from Jennifer. Jennifer would like to know, what was the motivation to complete the contracts as design, bid, build versus design, build?
You know, I mentioned earlier that the consent decree was settled in 2006, and so obviously to have the long-term control plan together for that consent decree occurred in the early 2000s, and I was not part of the program at the time, so I can only speculate. However, I don't know that in the tunneling world in North America, design build was being utilized for projects like this to that extent. Plus, I believe with a municipal owner at the time, the city of Indianapolis, design, bid, build is a known delivery method, and I could even go so far as to say it may not have been an authorized, design, build may not have been an authorized method in the state of Indiana at the time the consent decree was entered into. Our design, build that got written into Indiana code, I believe, may have come after that. So it was probably a combination of they knew what worked versus they may not have been allowed to.
Great, thank you for that. That looks like that's our only question. So we'll ask our attendees to please reach out to Mike using the email and contact information on the screen. Otherwise, we'll go ahead and wrap up today's session. Mike, thanks again for this great presentation. We've really loved your photos, and I think the majority of us related to the Millennium Falcon comet.
Oh, fellow nerds, I appreciate it. So
definitely equipment junkies.
yes.
So thank you everybody for joining us today, and we hope you can join us for the next UCA Young Members webinar on March 29th. Visit the UCA Young Members website for additional information on that webinar, and we hope you have a great day.